Thank you. Thank you. Okay. All right. Yeah. Thank you. So I will talk about something I have been kind of uh, thinking about for the last few years, and probably something I will think about for the next few years as well. So don't let the title scare you. I'm not going to even attempt to prove Vojta's conjecture or anything like that. But I will tell you a little bit about this and how I got even remotely attached a little bit to that problem. So this is the notation that is used normally in arithmetic geometry and algebraic number theory and so on. So don't worry too much about it if you haven't seen it before, okay? But I'm sure some of you are quite experts on this. So K is a number field, so a finite extension of the rational numbers. And OK, this script O of K is the ring of integers. MK will denote the set of all absolute values. And as usual, MK0 is the set of non-Archimedean ones, and MK infinity the set of Archimedean places. All right, so later on when we state the Vojta's conjecture, S will denote a finite set of places, okay, including all the Archimedean places. I will use this notation for every new place. We will denote this new plus, the maximum of, okay, so this is a typo here, mu of alpha and 0. So this is supposed to be this parenthesis supposed to end here. Okay, for all alpha in K. And normally h of alpha, which is the height, I'll talk more about this, will be basically the sum of all the places for this mu plus of alpha. This is the so-called absolute. Yeah, I think I can, maybe. Yes. I don't know. Is it better? Okay. I mean, I can, yeah, I probably can make it all full screen. I'm not sure. Okay. Okay. So let's see. So what does this Vojta's conjecture say? I mean, well, okay, I got obsessed now with this zooming thing. Okay, so we all know this Moore-Dale conjecture, which is kind of an old classical part of the folklore now. If you have an algebraic curve of genus bigger than 1, then it has finitely many rational points. This was an old conjecture, a very fascinating one, and it was proved in 1983 by Faltings, and it is called now a Faltings theorem. It was later generalized to any number field. I mean, this is the main game in number theory is you prove something over Q. I mean, the next natural question is, well, is it true over any number field, okay? But there was also something else here to be said. I mean, these algebraic curves are very particular kind of objects. They are so-called abelian varieties of dimension 1. And so, of course, the more general question is, well, can we somehow get the equivalence of this type of conjecture or theorem maybe for more general abelian varieties? And so Vojta's conjecture, it is kind of a natural extension of that type of thinking. And I should say that it's probably the most important conjecture in all of this type of business. It does imply the ABC conjecture and this Lang conjecture and Bombieri-Lang and all these types of, there are several conjectures on this type of things. I will not say much here, but all of these are related somehow to these heights, okay? So let me just read through this Vojta's conjecture without trying to explain most of the terminology there. And then we'll just see if we can explain some of them, and if we can make sense of them for these weighted projective heights, which are even more kind of complicated a little bit. Okay, so we have a number field. We have a non-singular, so smooth algebraic variety. Okay, and we have a divisor on X, an effective divisor, so a positive divisor on X. With that worst normal crossing. Now, if you know a little bit of geometry, you know why that is, okay? So we're talking about varieties of dimension bigger than one here, so you know they can have these singular things. Okay, so A is an ample divisor on it, and Kx is this canonical divisor. So now we have this Veil machinery, or this height functions a la Veil are called. So this height of this ample divisor and the height of the canonical divisor, okay, and the local height functions. So again, if you don't know what they are, I'll try to make some sense of them later. Okay, what this conjecture says is that if we have a finite set of absolute values, let's say S, and we have some epsilon positive, there is a constant, okay? There is a constant C, which depends on all these things that are given, and a non-empty Zariski open set U, okay, such that the sum for all the places in S of these local heights plus the height of the canonical divisor is less or equal to epsilon times the height of the ample divisor plus that constant C. And this is true for all these P, all the points P in that open set. So in some open set, these kind of heights are somewhat bounded. Now, why do we care about this? Why do we want to bound the heights, and what are really the heights that are, what are really the heights that, and what do they have anything to do with the rational points on a curve? I'll say more about this. But I want to bring you all to this picture. This was the first time I heard Paul Vojta talk. I believe it was in this ABC Arizona Winter School on ABC Conjecture on March 98. And he gave 3 lectures, Monday, whatever, Thursday, Friday, Saturday or something, 2 hours each, so very long lectures on Vojta's conjecture, basically, and all this stuff. And this picture is right after his talk. I remember I was lost very early on his lectures, and I remember he slept most of the time during the workshop. So either he talked or he slept most of it. But at the end of the talk, I'll ask for a little quiz if you can recognize any of these people. All right. So can I say something about these heights, right? They seem to be all over this Vojta's conjecture. So let's just say something about these heights. And then we go from there. So if for a point on non-zero point, okay, on a field, we define the height this way. We go through all the absolute norms, right, of that field, and we take the maximum of 1 and the norm of that element X evaluated at the norm mu, right? So this is really what the height is. If you ever taught an undergraduate number theory course, you probably have proved this Mordell-Weil conjecture for elliptic curves, and this is where you will first see this kind of stuff. Okay, and this height has also the logarithmic version of it, which you just take the log of this, and this vector now, this product becomes a sum. You can generalize this to a Cartesian product of K by taking what? You take the maximum of all these norms, okay, for all the coordinates. So take the maximum for each particular norm, you take the maximum among all the coordinates, and then, of course, you take the product, but now the product of these maximums. Honestly, to tell you the truth, there are 2 very good and very big books about this. One is by Mark Hindry and Silverman, and the other one is by Bombieri and I forget now, it's just Bombieri, I think. Anyway, so they have everything about this, and I mean, if you read through them, unless you get your hands dirty, they kind of don't make a whole lot of sense. They look a little bit artificial, but anyway, so now we can make these things over, define them over a projective space. And the way we define them over a projective space is here. So we define them over a projective space is exactly this. Every point in a projective space now is a tuple, but up to equivalence. We define them exactly like this. And one of the first things you show that they are well defined. So the height of a point in the projective space does not depend on this representative of the point that you take. So this is good because now once you define them on a projective space, well, maybe, just maybe, you can define them for all a billion varieties, which after all, at least every projective variety is embedded in a projective space, right? And hopefully you can use them for projective varieties. But this is maybe this theorem, which I didn't put it in the most elegant way here. It is the key to all of this. It's called Northcote's theorem, and it says that the number of points in a projective space, the number of points of bounded height is bounded. I mean, sorry, it's bounded, it's finite, I meant, okay? So I just typed this morning. It's finite. So if you fix the height, the number of all that points of height less than that bound, that upper bound, is bounded. What does that mean? If I were to try to prove Folting's theorem, okay, that the number of rational points on a curve is finite, all you have to do is to show that the height of all rational points is finite. And that's exactly how this game is played, and that's how they have been proved. Now, keep in mind, I'm defining a height this way, but actually these heights can be defined, and that's what Weil did, and that's what these heights a la Weil are called, this Weil machinery. You can define this for any norm, okay? So you can talk about these line bundles and all that stuff, and you can define different heights, and as long as they have certain properties, as long as they are height, this Northcote's theorem is true. And so that's why you hear, well, Folting's theorem, there is a Folting's height, and there is a Néron-Tate height, and GIT height, and all kinds of stuff, okay? All right. So now I want to talk a little bit about a paper of Silverman from 2005. And this paper is called Generalized Greatest Common Divisors, Divisibility Sequences, and Vojta's Conjecture, or blowups. Okay, so just look at the GCD of two numbers, okay, alpha and beta, and these numbers are integers over some number field. And this is how you, fancy definition of the GCD, right? I mean, that's how you would actually define the GCD of two numbers. So you go over all the primes of that ring of integers, and for every prime, you take the minimum of the valuation of that prime for both numbers. Okay, so if you have 6 and 8, and you take the prime in common is 2, so the valuation for at 6 is 1, and the valuation at 8 is 3, but you take the minimum, so you take 2 to the 1, and that is the GCD. For all the other primes, since they don't show up there, it's p to the 0, so the valuation is gone. Yes, and so, okay, there is a logarithmic version of this. You take the log of this, and now this product becomes a sum. There's nothing fancy here and nothing new, okay? But here is what
wait, do we need this to be multiplied by like log of p, or for the logarithmic greatest common divisor, right? You have the exponent here, but what about like the size of the prime itself? Or are we ignoring that?
Yeah, I mean, you just take the log of this, the log of the
right.
GCD.
Right. So it's the sum of
Oh,
the
yeah,
minimum, times
yeah,
log of p, or
yeah. But there
okay.
is this product formula, okay, because your product,
Oh,
you are going over all the absolute values, and the product formula will be one, and so that's why that doesn't show
right.
up.
Okay.
Yeah. Sorry, I
That
could
makes
have
sense.
explained it a little bit. Anyway, so what Silverman did, I mean, it just came up with this idea of, well, now maybe I can generalize this. And he's generalizing this log GCD by doing the following now. Instead of actually taking this sum, okay, of these minimum values, I'm taking the sum of this new plus that I defined earlier, which was the maximum of this one and the absolute value, okay? And so now, well, I mean, in this case, I mean, this mu plus can be looked as a height function, okay? But if you want a height function of the projective space, you have to make sure that, you take care of the point at infinity there. And so at infinity, you assign it to 0. So he defined this local height, call it G mu, this way, for any, so P1 cross P1, for any two A and B, keep in mind, he was dealing only with a GCD of two numbers, okay? So he wanted to play that out. For any two numbers A and B, he sent it to the minimum of this G plus, mu plus of A and mu plus of beta, right? Or whatever, A and B. Okay, then this local height that is defined this way, if he sums it up over all the absolute values, he should get the so-called global height. And that's what he defines a global height to that. So the whole idea was to actually express this height as in terms of these GCDs. Well, okay, that was fine. It did play a little bit with this now in terms of these blow-ups. So here is an example that is taken from his paper. So he basically said, if I take X now to be P1 cross P1, and I take a blow up pi from X tilde to X, okay? At the point 0, 0, I take the fiber of this point. So I take this exceptional divisor, okay? Then for all these points, other than the point 0, 0, right? So for all these points, the local point there, okay, with respect to this blow up and with respect to this exceptional divisor, which by the way, so X and E, right? Okay, the local point will be the minimum of these two values, mu plus and in alpha and beta. Okay, there is a little bit of details there to make sure that these things are not just hot air, but it works. Okay, so you have to check it a little bit, but once this is a local height, you can just add this up, okay, and define the so-called global height. So the global height now will be denoted by this one. It's a global height with respect to this blow up and this exceptional divisor. All right, so once you do this, okay, so he's able now to do what? To define, okay, to introduce this notion of this generalized log GCDs on a point on a smooth variety once it's given a subvariety and we have a blow up over that subvariety. So from this point of view, he is able now to write this Vojta's conjecture. So if we have X to be a smooth variety and Y, all of these things defined over some K, right? Some field, and Y a subvariety of this, and the codimension of Y is bigger or equal to 2. So now let pi be a blow up from X tilde to X along this Y, and Y tilde will be that exceptional divisor, so the fiber of Y, okay? Now A, as usual, is the ample divisor and Kx the canonical divisor. Here is what, and I haven't done anything here, okay, other than basically wrote the Vojta's conjecture now in this setup. So for every epsilon positive, there exists a Zariski closed set such that, okay, this cal z and a constant c epsilon, such that the sum of these local heights plus the height of the sum of the heights, I meant, plus the height on this canonical divisor is less or equal to epsilon times the height on the ample divisor plus that constant. Okay? So, well, but if we are going to say that the sum of these local ones, we are going to call it this global height, as we did before, then this Vojta's inequality or conjecture becomes something like this, right? So the global height on that blow up in that canonical, on that exceptional divisor for this given set S, right? Is plus the height of the canonical divisor is less than epsilon times the height of the ample divisor plus some c. All right, so far, this has nothing to do with me. So Silverman wrote basically this. So he said, if Vojta's conjecture is true, then I can kind of write that this way. So this got to be true, okay? So he was able to write this in terms of the blowups and these general GCDs, okay? What is it called? Generalized logarithmic GCDs. Okay. Now, at this time, around 2018 or so, I had actually, for different reasons, I was looking at the moduli space of curves, supraelliptic curves, and I was dealing with these sets of invariants. And I actually had defined something called the weighted GCD on weighted projective spaces. And later on, in a paper with Mandili and some AMS proceedings, and then later on, we had a paper on this Journal of Number Theory with Pesce and Gutierrez, where we defined these weighted greatest common divisors and weighted heights. And a couple of weeks after I posted that paper on Archives, Joe Silverman asked me if, well, what does that mean? Can these weighted GCDs be generalized the way that the normal GCDs are generalized? And will you be able to maybe state, if it makes any sense, but state now Vojta's conjecture in terms of these weighted heights for weighted projective varieties? And yeah, I thought this shouldn't take that long. So I started 3 or 4 years ago, I forget now, but I started and I was able to figure out very quickly how this should be generalized and how this Vojta's conjecture will look like in terms of these weighted projective heights. But in the process, I found out that almost nothing was done in terms of this heights, weighted heights and weighted spaces in terms of this machinery a la Veil, okay? So in order to define these heights, Veil heights in weighted in projective varieties, those of you who know, you need the Cartier divisors, and need all the analytical part of it to make it work. And none of these things were really there. They were not defined. We found a couple of papers where it was defined what a weighted projective space is and weighted variety, but that was about it. And so that's why this paper kind of became long, but we managed to somehow get through with that and redefine everything. So everything kind of works nice. Going through here, weighted polynomials and Stellensatz and what is the weighted ideal now and what's the Zariski topology on the weighted projective spaces and all of that. We had to do all of that, and we had to define all the Cartier divisors and all the global and local heights in order to make this work. So obviously that would take me a long time for any talk, not just for this one. So I will actually skip some of that. I should mention this. Yes, these weighted projective varieties can be embedded into a projective variety, okay? And there is this Veronese embedding. And this is nice because after all, we can look at them on a projective variety, but it has some big drawbacks, okay? And if I can get through this example, I will stop for the rest of the talk, I think. Yeah. So look, this is the case of genus 2 curves. So those of you who have worked with genus 2 curves, there are 4 invariants, J2, J6, J whatever, 4, 6, and 10. These are the weights of these invariants, 2, 4, 6, and 10, okay? You can embed them into a projective space this way. So you take the LCM, the least common multiple of this, and do all that. Now, this will be a point in the projective space. But now think about it. If somebody has computed these invariants of a binary sectic, so a degree 6 polynomial, these are huge. I mean, these are a couple of pages. Polynomials in all these coefficients, a couple of pages or more each. And if you raise that to a 30th degree power, I mean, this is almost impossible to deal with. Okay, and so what do? I mean, it is a nice way to do it, but it is really not really workable. So people had used all kinds of absolute invariants, and all of them had all kinds of ideas. And when I was trying to do some stuff with the arithmetic rational points in the moduli space of this, I realized anything else is kind of stupid. I mean, it does make sense to just stick with this. You want to somehow deal with this tuple of invariants. And by the way, I mean, just because you have a tuple might not be good enough, because think about if you have a common constant there that shows up, a lambda that shows up in lambda squared for the first coordinate, lambda to the 4th for the second, lambda to the 6th for the third, and lambda to the 10th for the last one. You can pull that lambda out. So for practical purposes, when I was trying to store this in a computer, I don't need, it's not good enough to just have a tuple of invariants. You just want the smallest tuple to say, I mean, the smallest representative, but smallest, taking the GCD out is not good enough. And that's why I came up with this idea of the weighted GCD. You have to take out things that don't mess up the moduli point. And once you come up with a weighted GCD idea, the kind of a weighted height, it is very normal, or very natural, I should say. So this is how the weighted height is defined. Okay, so here keep in mind the weights are Q0, Q1, Q2 to Qn. So now instead of taking the maximum of each one of these, we take the maximum, but each coordinate has to be raised to the power 1 over Qi. And I was shocked to see how after this, I mean, things work like magic. Everything works fine. And I'm still a little bit surprised how this has not come up in the literature before. But anyway, obviously I cannot go through some of this stuff. I mean, but I would like to say the following, and I'll stop. Here is now this analytic version of the Weyl height, but now for the weighted heights, okay? And we have a proposition that it satisfies the necessary properties for things to work out. And here is now the definition of the global height, okay? Again, through these line bundles and Cartier divisors and all that, and these are the properties of that. So the whole point is, yes, everything works out. And here is now Vojta's conjecture for the weighted varieties. No big surprise here. Once you define the weighted heights, it seems like it's fine, really. I mean, everything is what you expect it to be. And then we go ahead and do this, generalize this weighted GCDs. And I mean, this has been posted, so you can look at it. I will just show you the last two things. Okay, so here is basically what that local thing, that local divisor there given in terms of this GV that Silverman did, that's how that looks now. So this minimum of V mu pluses, now you have to divide by the height, and you have to take the integer part of that. So this is the necessary adjustment for things to work out. And so this is the general let me see, the general logarithmic weighted GCD, okay? To stick with the Silverman's notation. Okay, so the definition again of the logarithmic weighted GCD, I will skip the exam. Here is basically the analog of what Silverman proved there, assuming Vojta's conjecture, but now with this adjusted heights and adjusted weighted GCDs and so on. And okay, this is another version of it, still assuming the Vojta's conjecture, but I will stop here. Thank you, and sorry it took a little bit long. All right. I still would like to know how people recognize anybody here.
I think I see Kiran Kedlaya.
Ron, Manjul, is that
This one here in blue shirt, this is Henry Darmon.
oh yeah.
Yeah, and this one here, I believe, is King Leo.
Right. It's that
Joe
strange looking dude
Weatherall.
in the striped t-shirt behind Darman between
yeah, that's me,
Manjul
right?
yeah.
yeah, that's me. And then Manjul and Kiran and Joe Weatherall, I believe, is this guy sitting here. I don't remember the rest, but anyway. Okay. All right. All right. Thank you.
I have a question actually.
Yes, please.
Yeah. And I would like to ask if, okay, weighted projective spaces are in general singular. So I would like to ask if these singularities bring a lot of complications in your treatment with respect to the smooth case.
Well, I mean, sorry, it does. I'm trying to bring up the Zoom, okay? Look, I mean, the original Vojta thing is, so you have a problem there. I mean, Vojta's conjecture is done for, oh, here, now I understand why. Vojta's conjecture is stated for the smooth curves. Now, of course, I mean, smooth varieties. I mean, of course, you can adjust it and whether that you can, problems will that create for the weighted projective varieties? I'm not sure, but I'm sure that somehow so far I have not seen any surprises. Anything that works in the projective case, it kind of works over. So most of the difficulties are things are not defined, as you have to do a little bit of work to kind of, build it up.
Maybe you can do the same thing for varieties which are locally the same as weighted projective spaces or not? You really need the global weighted projective structure, or just something related to the local nature of singularities?
For what?
For doing your extension of Vojta conjecture.
Well, I mean, so the Vojta's conjecture is expressed in terms of the global height, but yeah, so I don't know. I mean, if you can, I haven't seen a version of it where you can just talk about singular varieties. I mean, try to state the Vojta's conjecture for singular varieties, but I wouldn't be surprised if it is done. And I'm talking for the projective case. Yeah.
Because
so,
this singularity, I think, has very special. They are cycling quotient singularities, right?
Yeah, I think. Yeah, well, let me. I take it back. There is a paper by Yasukubu or Yakubu or something that has a version of this for singular varieties, a version of the Vojta's conjecture. I actually have seen the paper, but not in detail because it was we didn't go there and it would be too much. But yes, I know there is something. I know for sure there is something that deals with the singular varieties, and yeah, that will be another pain in the neck to try to take that and have a version of the weighted projective varieties with that adjustment, but it probably can be done.
Thank you.
Yeah. Thank you. Thank you. Thank you very much. All right, thanks. I think now the next one is so Kidas, right? Did I say it right?
Almost perfect.
Oh, almost. Okay.
And also the name is written in Greek, so I don't.
Right,
in
right. Yes, yes, that's right. I try to guess that. Okay, so I'll make you co-host, and if you can try to share the slides and see if we